This video is about elastic curve of engineering structures. During the design of an engineering structure, we do not only consider the strength, but the deformation of the structure under loads. That means the rigidity of the structure is also important. So there will be elements working together made of materials with different rigidity, and it's important to consider the deflections and to ensure their compatibility. Well, for interdeterminate systems, the compatibility equations written for deflections at specific points can also be used to analyze the structure. Well, for all these reasons, we draw the elastic curve. For example, let's take a beam, and the elastic curve gives us the deflections at different points. If this is the distance x, v as a function of x is my elastic curve. The elastic curve is obtained by plotting the position of the centroid of the beam along the longitudinal axis. So in each point we have a section, and each section has a centroid, and the elastic curve is the position of the centroids along the longitudinal axis. So the elastic curve must fulfill some boundary conditions. For example, if you have pins in the structure, so pins are supports that resists a force. Well, here in these points, the displacement is restricted. V equals to 0. V equals to 0. If we have a support which resists the moment, for example, a fixed support, in this case, at this fixed support, V equals to 0, and the slope of the curve dv over dx is also 0. So the displacement and the rotation are both restricted. In order to find the mathematical expression of the elastic curve, we can derive the following expression. This expression gives me the relation between the internal moment and the radius of the curvature, and also the material's elastic modulus and the section's moment of inertia are also given. We will not derive this formula, but use it when we have this formula. We also know in a curvature, well, this 1 over rho value is equal to the second derivative of the curve. So if the deflections and the slope of the curve are small, well, we can mathematically approximate this curve with this expression. Here, V is the deflection at the relevant point of the elastic curve. So if we rearrange this equation, so we have the second derivative of the deflection. These are the section and material values, and this is the acting bending moment. So this is my starting point. We also know the relationship between the bending moment and the shear force and the distributed load. So these three equations are, this is the second derivative of V, this one is the third, and that one is the fourth derivative of V. So if we know the bending moment or the shear force or the distributed load along the curve as a function of x. So we can start with one of these equations. You see these equations starting with m, with v or w, and making multiple integrations. You can find the v f x function. Generally, the double integration of the moment equation is used because double integration is much more easier than the other methods. So by double integration, you will have two integration constant, and these can be determined with the help of the boundary conditions. Well, what are the boundary conditions? As mentioned before, if you have pinned supports where V is restricted, the beam is free to rotate. If you have a pin support, well, the deflection is restricted and also the rotation is restricted. The slope will not change. If you have a free end on a beam, here you have the shear force and the bending moment equal to 0. Well, an example, you see a fixed support and the force P is acting, so we need the function of this elastic curve. We need a Vx function. The first thing we do is to cut here, for example. If you cut, so this is your function. So if you take the left side and using this free body diagram, you can find that m equals to minus px. You see, this is the correct direction of the x, and it has a negative value, and m is equal to e times I d square v dx square, and this is my function where I have to start my integration. If the double integration is applied, dv over dx and v function is obtained, you have two integration constants. Well, these are my two equations for the slope and for the deflection. These are my constants. Boundary conditions. In point B, v equals to 0, dv over dx equal to 0, because a fixed support restricts the deflection, also restricts the rotation. So if for x equal to L, dv over dx is 0, so you put a 0 here, you find C1. Now the second boundary condition for x equal L, deflection must be 0, and you find also the value of C2. Well, these are the equations for your deflection and slope of the curve, and the curve will look like this, and putting the x value you can find for each point the deflection and the slope of the elastic curve. Well, in summary, when you use a double integration method, well, you draw a draft for the beam's elastic curve. You know the boundary conditions, you can just draw a draft. Having this draft, you choose your x and v coordinate axis. And, well, we prefer to express the moment m as a function of x. You can also find V and W and V values as a function of X, then you have to integrate more than 2 times. But when you start with M, you just make the double integration. Well, if E times I along the beam is constant, that means the material is same, the section's moment of inertia is constant, so you can make then the integration easily, and you have to calculate the integration constant by using the boundary conditions. And if you have the constants, so you can have the equations for the slope and deflections, and for each point you can determine the deflection and slope. So the obtained results, if you have the numerical values, well, it's recommended to draw the curve and you to check graphically and compare it with the draft drawing of the elastic curve. Another example, here we have a supported beam. An external force is acting. The cross section is a rectangular cross section. So by using the equilibrium equations, you can find that RA and RC values are 100 and 200 respectively, and then start to draw the elastic curve. The elastic curve will look like something like that. Here we have a maximum. The maximum is not in the middle because that 300 Newton is acting to the right, so the maximum must be somewhere on the right side of the middle section. Next, before we start calculating, let's determine the moment of inertia for this section. And for the integration, we need this product, that is the elastic modulus of the wood, and this is my I value, which I have calculated over here. So E times I is this value. Now we look at the beam, so we have to express the moment as a function of x. But as you see, there are two segments. The first segment is AB and the second segment is BC. So we have to make our calculations for these two different regions, and probably the curves for these two regions will not be the same. So when I cut in the first region, so over here, and here take the left side, so this M can be written as 100x. And when I cut on the segment BC, this time the expression of the moment will have this form. So we have two equations for the moment. For 0 to 2 meters, region 1, this region, and from 2 to 3 meters, the second region. Okay, now double integration for section AB, this section, this is my M value, and starting with this first integration, second integration, you see we have two integration constant. This is done for AB. Doing the same for BC on the second segment, the curve, the M function is given as 100x minus 300x minus 2, double integration, and we have additional integration constants. So we have 4 integration constants. So we have to use the boundary conditions. Well, these are my equations and my integration constants. So the boundary conditions. Well, the easiest boundary condition is for x equal to 0 this point, deflection is 0. For x equals 3 meters, point C, the deflection is 0. Okay. In this curve and in this curve, for x I put is 0, and these two boundary conditions give me these two equations. Well, additional boundary conditions are for point B. You see point B is on the curve AB and also on the curve BC. Well, this point B has a deflection V, and this V value, when you calculate it for AB or BC, these must be the same. That means, and also the slope at this point for both curves must be the same. So for x on the left and for x 2 meters on the right, the slopes must be the same. So this slope and this slope must be equal for x equal to 2. And also the deflections at the same point for x 2 meter left, x 2 meter right. So if you put these equations, that means this and this equal for x2, you will find the third and the fourth curves. These two were my previous boundary conditions. Now you have 4 unknowns and 4 equations, so we can solve easily C1, C2, C3, and C4, and by placing the constant into the equations, you find the expression of the deflection curve on the left side and on the right side, and also the slopes of these curves. The question is to find the displacement where the maximum is reached, that is somewhere at a distance x from the axis. In order to find this point, well, we know this maximum is where the slope is 0, dv over dx, or v prime is 0. It is on the left side, and this is the curve, and when I have put 0, I can find the x value as 1.63, and if I need the value of deflection, I take this x and put it into the deflection formula, and I find that the deflection is -7, so it is negative because it is displaced downwards. My delta is 7.09 millimeters. Another example, well, we have a beam. The beam has a steel profile and its catalog values are given. In the catalog, you have the moment of inertia for the section and the S value. This is the section modulus. This is the elastic modulus of steel, and where we have a length of 3 meters and the distributed force is 60 Newton meter. Okay, find the maximum stress and the displacement values. If you look at the beam, you find out that the maximum stress is here, it's very clear, and the maximum deflection is here, maximum deflection. Okay, the first thing we have to do is find the moment by using the equilibrium. For a distance of x, I cut here, take the left side. For this distributed force, I put effective force in the middle, Wx, having a distance x over 2, and my m value will be minus W0x squared over 2, and my equation for double integration will be like this. And by doubling integration of this equation, I find these two, and as you see, I have two integration constants. So the boundary conditions are for x equals L, that's this point. Well, you see we have a fixed support here. dv over dx is equal to 0, and v is also equal to 0. With the help of the first boundary condition, I find C1. With the second one, where the deflection is also 0, I find the second integration constant. Using the constants, I have the deflection and the slope curves. So, where is the maximum displacement? Well, it is when x equal to 0, this point. So I've put x equal to 0, and here 0 is 0, and if you calculate the delta, which is the absolute value of v, you find that is approximately 3 millimeters. The deflection of the beam at point A is 303. So the maximum stress was asked, that is this point. Over here, the m value is the bending moment is, well, you can put WL over here, that is L over 2, and the value of m can be calculated as W0L squared over 2, and the sigma max for bending is m max divided by the section modulus, or you can write it also minus m y over I, and this value is S equals to I over y, and so it's the same formula, and putting the values into the equation using the numericals, you find that the stress in point B is sigma 3.375, and since it's bending on the upper surface, we will have a plus maximum, and in the lower surface, we will have a compression maximum stress value. And as a last slide, well, we use superposition for our stress calculations. For our deflection calculations, you can also use the superposition. For example, in this beam, you have a distributed load and you have a single load. So you calculate, for example, for point B, you calculate the deflection for the distributed load and separately the deflections for the single load P, and their sum will be equal to the deflection if both loadings are applied at the same time. So superposition will help us also in calculating deflection values. Okay, this was our video about elastic curve, and we have solved a couple examples. I hope it will be useful, and thank you for listening.